All right, let's continue on the lecture here. I'll finish this impulse response today. Maybe we'll have 20 minutes left, and we'll start a new topic on Fourier series. So just continuing the examples we did previous, okay? Okay, I need to correct one of my mistakes from previous example, and also maybe just some words about the caution of the symbols used in the example. Okay. First of all, we use symbols, not necessarily the same symbols stick to the same thing. So we always talk about input, output. So which variable represents an input, which variable represents the output, and that's what you need to be very clear for the question here. Okay. So for this question, for example, this is input, and this one is the output, right? So this is the two symbols in here. And for the second order differential equation, of course, you get this second order differential equation after you plug in the MBK. Okay. So then you get this. So the first question is looking for the transfer function. Transfer function is the ratio between the outputs over the input. Okay. I think in the previous lecture I wrote it as F over X. Right, so that was a mistake. Although the answer was right, but the impulse response, the transfer function should be the ratio between the output over the input. Okay. And when you take the Laplace of both sides of this, you get S squared capital X of S, 4S capital X of S, and 5 capital X of S equal to F of S. So the ratio you get, which is the transfer function, is 1 over S squared plus 4S plus 5. Okay. Yeah, just to make sure that you know which one is input, which one is output, then you find the ratio appropriately. So from here you can find the impulse response by taking the inverse Laplace of this transfer function, and then you get e to the power negative 2t sine t times u of t. Okay? Yeah. The third part of the question is, okay, if f of a t is a unit step function and also initial conditions are given like this. So let's solve for the output x of t. Okay. So you do exactly the same approach, taking Laplace transform of both sides of this equation. But now this time, because you're not looking for transfer function anymore, so then you need to incorporate this initial condition when you're taking Laplace of the second order and the first order derivatives. Okay. So I think I did all of this in the previous lecture, but you will get your x of s equal to this. Okay. So you're going to get x of x equal to this, and then you take partial fraction expansion. There are two fractions, two terms in the numerator. One is s, the other is s squared plus 4s plus 5. And the solution for this quadratic one turned out to be a complex conjugate number. So your partial fraction expansion accordingly has to be in this format. Okay. So once you get this, then you can use comparing coefficient approach to calculate constant ABC's value. And A turned out to be 1/5. B equal, what is it? Negative 1/5. C equal to 6/5. Alright, so you're going to get this constant's value. So the next step is to take the inverse of x of s to get x of t. However, okay, you're going to have to do something first before you can get the inverse of x of s. Okay. Especially the second term here, in the second term. So I'll show you again. Okay, this is approach I think I have emphasized. The first term is 1/5 1/s. Second term, okay, is negative 1/5 s plus 6/5 s squared plus 4s plus 5. Okay. So let's take a look at how do we manipulate the second term so that we can make use of the table. Okay, so let me open the table right here, Laplace. Okay, the idea is over here. Okay, so these two are our ultimate objective. We manipulate to fit into these two forms. So first one, okay, let's write down the bottom first. Okay, let's write down the bottom so we know what we should do. So the bottom is s plus 2 squared and plus 1 squared. Okay. And if I want to make use of the table here, I need a numerator to be s plus a, or I need a numerator to be omega. So I need s plus 2 at here, right? So right now it's just s, not s plus 2. So what do I have to do then, right? I'm going to take that negative 1/5, okay, out of the picture here. So if I take this out of the picture at here and keep this s as s plus 2, then technically I should do what? I should add a 2 plus 5 at here, right? Yeah. Let's temporarily do this. Sorry. Let's temporarily put this over here, okay? Yeah. In order to make it unchanged, so we have to add a 2/5, right, to stick to the negative 1/5 s, and then 6/5. So this time I can separate the second term into two terms. One is s plus 2 over s plus 2 squared plus 1 squared. The other one is, this is 8/5. Leave it as 1 at the top. Okay? Yeah. So this time, you have exactly the same format as what's in the table, Laplace transformation table. Okay. So you're ready to take the inverse now. First term is 1/5 u of t, so I'll keep the u of t on the outside here. And this is negative 1/5 e to the power of negative 2t. What's this? Cosine omega t. And cosine t. a over 5 sine t. Right there. So that's your x of t at here. So this is the system output when input is a unit step input and under the given initial conditions. Okay? Yeah. So this example basically goes through three different stages, right? Number one is not looking for an output solution, just looking for transfer function. Number two, looking for impulse response, which is still not the actual system solution, right? Based on certain inputs. So impulse response is the response when input is impulse. And the third part of the question is when the input is actually a specific input, not an impulse response anymore, and how do you get the actual output, right? Based on the techniques of solving through the Laplace transform. Okay, so that's that example, okay? Yeah. I have one more topic and to finish, which more of a review of this one here, okay? More of a connecting the dots. So let's use more of a generic equation at here, okay, to look at this. So let's say consider we have a y double prime plus ay prime plus by equal to f of t. So let's look at this general second order differential equation with an input f of t. Initial condition C and D. Okay, so a lot of symbols here, no numbers, huh? Yeah. So A, B's are the system parameters. C, D are the initial conditions. So what will be the solution for this second order differential equation? Okay, so let's take a look at it. Again, we're going to take a Laplace transform of this equation. We get s squared y of s s times y of 0 y prime of 0 and a times s y of s minus y of 0 b times y of s and then capital F of s. Okay, you take Laplace transform. Now we're going to group similar terms. Group all of the y of s term. We get s squared as plus b. Okay. And then minus all of the other constant terms, not constant, the other terms associated with the initial conditions, which we will get that's weird. We'll get s plus a y of 0 and then minus y prime of 0, okay, equal to f of s. Okay, so I'm intentionally writing two different color sets here. Okay, yeah, and I want to see why. The blue color, okay, is the portion as if there's no initial conditions, right? The red color comes solely from initial conditions. So if your initial condition is 0, then you don't have these two terms, basically. You will have just this. right? And then basically you're going to get the transfer function, right? Yeah. So now I'm looking for the solution, right? So looking for the solution, I can replace this y naught with c, this y prime naught with d, and that's fine. So I will get a solution for y of s, and essentially your y of s will have two terms. One term, the red one, is s plus a times c minus d over s squared as plus b, and then plus the other term. Okay, so your solution for y of s has two terms. One term is completely determined by initial condition. The other term is completely determined by the transfer function and the input. Right, so this is basically the transfer function times input. This is essentially due to initial condition. Okay. Yeah. So it's like you have two different s function. If we call the first one is y1 and the second one is y2. Right. So your y of s is like the addition of these two s functions. Okay. And if you're going to try to get y of t, okay, which is the inverse Laplace, so basically means you're going to try to get, okay, the inverse of the first one. Let's use the red color. And the inverse Laplace of the second one. Okay. Yeah. So let's say I call the first one as y1 of t. The second one I call it y2 of t. Okay, right? So your solution, basically, up to this, you can understand now. The solution of the system depends on two different parts. One part, this is due to the initial condition. The other part is due to the transfer function times the input, or in other words, due to the input. Okay, yeah. So what is the second part, right? Before we make a conclusion here, let's look at the second part at here. Second part. So the second part, y2 of t. Equal to the inverse of, okay, let me rewrite that over there. Okay, equal to this, right? And the first s function, this part of s function, is basically, as I said, is your transfer function. It's basically the transfer function. Okay. So you're taking inverse of the multiplication of the transfer function times the input Laplace transform. Yes, input Laplace transform. Okay. So according to the Laplace property, when you have a 2s function multiplying together, and then you're taking the inverse Laplace, the results equal to convolution. Right? Equal to the convoluted inputs with the impulse response. Okay? So this is the second part, right? Now remember when we introduced the concept of impulse response, and I said if you have the impulse response, then your output will be just any current input convolute this impulse response. Okay? So right now, what happens is your input actually has due to initial condition and due to this impulse, due to the actual input convolute the impulse response. Okay. So this is basically a general conclusion at here. So the y of t, okay, we call the y1 of t. So this one here, we call it natural response. Okay. Natural response basically is the solution due to initial values. So it's called a natural response. So the wording is very simple. I mean, really, it doesn't matter whether you have input or not to the system. If you have a initial condition initially, then the system will have this natural response, right, due to the initial condition. And the y2 of t, we call it the forced response. Okay. So the forced response is this part. That's due to the input. Okay. And this is actually a particular solution because it is due to the f of t, right? It's due to this input here and following zero initial conditions, right? If you look at the second term, there is no initial conditions involved at here, right? And this is true for any system. Okay, linear system here. Your output will always consist of two parts. One part is the natural response, another part is the forced response. In most of the time, the natural response will disappear. Let's say you have a RC circuit and the capacitor is charged at the beginning. Okay? Now, if you don't do anything, what happens is the charge will basically discharge and go back to zero, right? Yeah. So that process of discharge is the natural response. So natural response most of the time will go to zero, will settle down. A forced response is a different story. It really depends on the system input, okay? And also depends on the system characteristics. Okay? So you could have a stable system, you could have an unstable system. Okay? Yeah. Now this actually brings a question when you learn control system. A very important question essentially is whether you have a stable system or not. Okay? So if you look at the second part of the response, right? What's the critical part? Of course, input is one part. Another critical is this term, which is the transfer function, isn't it, right? And the transfer function over here has a denominator. Now the denominator, right, will give you a solution if you set it equal to 0. If you recall that the solution for denominator, we call it what? Poles, right? We have a poles of the system. And the solution of y of t very much depends on the location of the poles, right? So for example, if the poles P1, P2 has two poles at here. Let's say you have 2 poles, right? And maybe the poles one is S plus 1, the other is S minus 2. Is that possible? Right? That's possible. Okay. So if I have these 2 poles, and then I take the partial fraction expansion, you get. Okay. You do this, And then you get a and b, and then you take the inverse Laplace. So for the first one, you get e to the power negative t. For the second one, you get e to the power of what? 2t, right? Okay. So if you look at the first one, as t goes to infinite, this one goes to 0. But if you look at the second one, at t goes to infinite, this one goes to infinite. Okay. So this is a unstable pole. You look at this one here, s equal to, this is called unstable pole here. Okay. Because this pole will result in a unstable response as t goes to infinite. And this pole, okay, at here on the complex plane, where is this pole? It's on the right side of the imaginary complex plane. This is the real part, this is imaginary part. So essentially, actually, there's a conclusion you will learn later, you can study more. When you have a pole that is on the right side of the S-plane, right side basically on the right side of the imaginary axis, okay, and you're going to have an unstable system. If all of the poles are on the left side, then you actually will have a stable system. Okay. So that's the nature of a characteristic equation. That's why sometimes it's important to look at the transfer function, to look at the impulse response, and then you have a pretty solid idea whether it's a stable system or unstable system. Okay. Okay, so that basically wrap up with the Laplace transform, application Laplace transform, impulse response, and up to this summary of what exactly behind a typical response for a second order ODE. Okay, there are two parts. Any questions so far? Okay. Okay. Now the last part of the course is another topic. It's called Fourier series and Fourier transform. And if you're going to study electrical engineering, if I don't do this, and you will have a hard time, and then the teacher will come back to them, how come you're not teaching them in the second year? So this is an important topic, okay, especially for electrical students. Okay, yeah. And after this one, we'll have another one called Fourier transform. So Fourier is a French mathematician, Joseph Fourier, roughly in the 1767 to 18 something. Very, very prolific mathematicians, produced a number of important theories and principles. And Fourier theories is one of this. Okay, and also Fourier transform. Okay, and it turned out to be so much useful in so many areas, okay, including digital signal processing, image processing, and some little things which I'll show you. Okay, yeah. Okay, so what is Fourier series? But before we introduce the Fourier series, I want to basically introduce a little bit of concept here. Okay, yeah. First of all, Taylor series. Okay, go back to Taylor series. If I'm going to get the Taylor series for function f of t around t equal to 0, okay, so you get a summation essentially n equal to 0 here, nth order derivative divided by n factorial, and then times t to the power of n. Okay. So that's Taylor series. I'm sure you have used it, okay? But I want to connect a couple dots at it here, okay? Now, if you expand this Taylor series, so you get basically something here something here, and something here, right? So you get some coefficient times t to the power 0, some coefficient times t to the power 1, right? And some coefficient times t to the power n, and you can keep going. All right? Yeah. Now what this one does essentially, if you look at this one here, right? Essentially you find, so this is a this is approach to approximate this f of t, first of all. Okay, so you're using an alternative way to describe this f of t. It's a little bit lengthy way, right? You're using infinite number terms to represent this f of t. Okay. If you use finite number of terms, then it's approximation. Right? If it's an infinite number of terms, then it's actually the same as f of t. And the other thing is, the nature of this expression, you look at this one here, right? You're approximating of this one as what? As a sum, as an infinite sum of some kind of coefficients. Okay, so there's a lot of coefficients here. And then times the Tn term. So the Tn term, mathematically we call that monomial. Okay. So this is the math behind this. If I describe it, right? This is basically what's going on here. You're trying to approximate f of t using, let's say, finite number of terms, and all of the terms are some kind of coefficient times those Tn terms. Does that make sense? Right? Yeah. Okay. So now back to the idea is, do we have other ways to approximate f of t? Right? It is the only way to approximate f of t. Okay. So before we think about other ways, which actually probably will guess now, okay, another way must be Fourier series, right? Yeah. Now before we talk about that, let's get back to the linear algebra a little bit backwards here, okay? In linear algebra, you learn, matrix multiplication, matrix inverse, eigenvalue, all of these things, right? Yeah. But there's one thing. There's actually the essential, the essence of linear algebra, right? It's all about what? It's all about vector space, isn't it, right? It's all about vector space. And when you talk about vector space, so one of the things you always talk about is, for example, right? We have, let's see, x, y, z plane. Okay, we have x, y, z plane. How do I describe x, y plane? I hat, j hat, k hat. And I hat is 1, 0, 0. J hat 0, 1, 0. K hat 0, 0, 1. Okay? So now, if I ask you, can you express this vector OA? So what do? So the vector OA equal to x times I hat plus y times j hat, and then z times k hat. Does that make sense? So basically here, this is a vector space. This is a vector space. Then what is I hat, j hat, k hat? the I hat, j hat, k hat is called, they are called what? If you recall that, the basis of the vector space. Okay? So now you can express any vector in the vector space using this expression. So use this times the basis, this times the basis, and this times the base, then you get the vector, right? Yeah. So I want you to change your perspective a little bit here. This is a vector, okay? That's fine. This is not a vector, right? But I can consider this T0, T1, T2, Tn the same word as basis. I can consider this as a basis, 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 basis. Then I'm expressing this f of t using something times this base, something times this basis, and something this base, which is exactly the same format as this. Right? So basically those T0, T1, T2, and Tn is also a kind of a basis at here. Okay? So they are the basis of f of t. Just like I hat, j hat, k hat are the basis of the vector OA. That makes sense, right? So I'm connecting two informations here, okay? So making an analogy here. One is the linear algebra, this, okay, how do you express something out of the basis? Mathematical Taylor series, how do you express f of t out of this basis? Okay? So the Fourier series, right? Without first I'll write it down, and then I won't do anything for now. Okay. So for Fourier series, okay, it deals with periodic function. Let's call it f of t. Okay, it deals with periodic function. And approximates f of t as this. Approximate this f of t like this. Here's infinite. That's what I told. Yeah, this thing turned off itself somehow. Let's focus on this side here. And if you replace the infinite sign with, let's say, a finite number n, then you're approximating this f of t. Okay. Now, do you see the reason I'm going through these topics at the beginning? What do you see at here? F of t is basically, if you expand this summation, it's basically equal to what? Some of the kind of coefficient times cosine n omega naught t, or let's use n, this is 1. And another coefficient times cosine maybe 2 omega naught t. And there's also sine omega naught t. There's also sine omega 2 omega naught t. And possibly more terms, of course. Okay. So your f of t is being replaced with a summation of a set of coefficient times each one of the cosine and sine at here. You see the similarity at here, right? Taylor series is you're replacing f of t with a sum of coefficient times the t terms. Fourier series is trying to replace f of t with coefficient times sine or cosine terms. So this basically means that here, if I use the similarity, so those cosine n omega naught t and sine n omega naught t, okay, different n numbers, they are the basis for the periodic function f of t. Okay. So the Fourier basically find a different way of expressing this f of t, in this case, a periodic function, using a basis of cosine and sine. Now, if you're genius, you might actually find a different basis, right? Mathematically, there are infinite way of describing a vector space. Okay. Yeah. So the question here is, okay, what we're going to do is we're going to study what's the significance of this. Okay. Actually, you probably already can see the significance, because you can see that you can literally use a periodic function sine cosine to approximate any periodic function. And if f of t could be the geometry of f of t could be just a line, or just an arbitrary maybe curve, right? But as long as it's periodic, you can always decompose that into individual sine and cosines. You add them up, you get back to this f of t. Okay. So in other words, as a matter of fact, as we're talking, the way I talk, the sound you hear, the noise you hear, anything in the back of the signal, what's there? You have lots of sine and cosine in the back, okay, which add up. Okay. If you play piano, you play the chord, you play a sound, okay, or K, there's sinusoidal signal behind it, essentially. Okay. How beautiful it sounds depends on the combination of the sinusoidal. Right? And those masterpiece has a good combination, right? And the way I play, there's bad combination. Anyway, so we want to study this, but I need to also have to go backward a little bit at here, okay, in order to get a better understanding of this Fourier series here. Okay, so I need to basically cover a couple of simple concepts at here. So let's step back a little bit, okay, and then we'll come back to this formula. So there's some basically concept I need to cover. The first concept I need to cover is called orthogonal function. Okay, orthogonal functions. Okay, so before we talk about orthogonal functions, how about orthogonal vectors first? Okay. So let's say I have two vectors, u and v. So let's say given these two vectors. And now I will do the dot product between the two vectors. So dot product is ui, vi, right, and I from 1 to n. Okay, so you get the dot product. And this is also called inner product, right? Okay, the inner product, the cross product is called outer product. If the dot product equal to 0, then we get the u perpendicular to v. So this is essentially what we call these two vectors are orthogonal to each other. Okay, that's the meaning of orthogonal when it comes to vectors, right? Vectors here. How about the function, right? So if I have two functions, f of t and g of t. Okay. So let's say we have two functions here. Okay. And if we integrate, okay, from a to b, integrate the multiplication of the two functions. Okay, that's a very simple integration, right? If this is 0, okay, if this integration is 0, then we actually see that this f of t and g of t, they are orthogonal over a to b. Okay. So basically, the concept of orthogonal can be transferred or moved exactly for the functions. So instead of vectors, we also have the exact same idea for function. So if I consider f of t, g of t like two vectors, right? So this quantity at here, so this one here is also called the inner product. The inner product of the two functions. So very much like this. Mathematically, you can write f dot g and equal to this integral. Okay, so that's called the inner product or dot product, right? And with this dot product equal to 0, we call these two functions are orthogonal. So like a perpendicular here, but this is not an actual perpendicular geometry, right? Okay, yeah. That makes sense? Okay, good. So now let's take a look at what are the type of functions that are actually orthogonal to each other, right? So consider the following set of functions. 1 cosine omega naught t, cosine 2 omega naught t, cosine, okay, and dot dot, cosine n omega naught t, sine omega naught t, sine 2 omega naught t, dot dot, sine n omega naught t. Right. So let's consider this set of functions at here. So within this big brackets, there are a lot of functions, sine, cosine, including the constant 1. And this function at here, which I don't have time anymore, I'll show you in the next lecture. So these functions, when you pick 2 out of it, and you do the integral, you'll find that, okay, not always, there's some conditions applied, they are actually orthogonal to each other. Okay, yeah. Okay, so I'll talk about it more in the next lecture. Okay.